Hello everybody. Today's lecture is about quantitative interpretation of seismic. You have heard from me how to do a structural interpretation, and we also have done stratigraphic interpretation. But today is the time when we will be talking about rock physics and interpretation. We'll quantify seismic and we'll introduce the concept of amplitude variation with offset. Amplitude is an important phenomenon in seismic interpretation which has led to understand the oil pools, the gas pools, and hence we'll try to quantify it in terms of the amplitude versus the incidence. We'll talk about a couple of AVOs, AVO sand 1, AVO sand 2, AVO sand 3 and AVO sand 4. We'll be talking about Poisson's ratio, where the involvement of the P velocity and the S velocity is important, and we will try to see how Poisson's ratio plays an important role in the quantitative interpretation. We understand that the sands inside the subsurface are encased within shale. The variation of the sand is very important as far as whether they are dry sand, whether they are wet sand, and how is the wetting happened. Is the wetting happened due to water or due to hydrocarbon? Within the hydrocarbon also we have oil-rich sand, we have gas-rich sand, and all these concepts will be brought to you to classify AVO and to understand the sand quality in terms of hydrocarbon presence. We have talked in the introductory lectures that velocity and density are important factors in understanding the porosity and the properties of the fluid which is there in the pores. You understand the pores can be filled with water, the pores can be filled with gas, and the pores can be filled with oil. Gas within the pore space of a plastic rock lowers the P wave velocity substantially but leaves the S wave velocity unaffected. Thus, gas entering the pore space of a reservoir affects the reflection coefficient at the top and bottom of the reservoir. We know that the reflection coefficient can be positive, the reflection coefficient can be negative. We have seen that density and velocity is acoustic impedance. So, when a boundary is there is a change in acoustic impedance. If rho to V2, that is the density or velocity of the second layer, is more than the density and velocity of the first layer, then rho to V2 minus rho 1 V1 by rho to V2 plus rho 1 V1 is the reflection coefficient across the boundary. Thus, gas entering the pore space of a reservoir affects the reflection coefficient at the top and bottom of the reservoir because of the phenomena which is the reflection coefficient change. The reflection coefficient will be positive if rho to V2 is greater than rho 1 V1. The reflection coefficient will be negative if rho to V2 is less than rho 1 V1. These effects can be used as direct hydrocarbon indicators, also known as DHI. Confidence in the accuracy of DHI identification can be done through modeling, and we understand that Thomson-Russell's method of understanding DHI is very important, and we will classify DHIs as a bright spot, dim spot and flat spot based on the amplitude and how it is varying with offset. A direct hydrocarbon indicator is an anomalous seismic attribute value or a pattern that could be explained by the presence of hydrocarbon in oil and gas reservoir. DHIs has a couple of aspects to be understood from the geological risks of the hydrocarbon, and some of the important aspects are the terminology, seismic data quality, rock data in terms of quantity and quality, use of all geophysical tools to understand where are the sweet spots and integrate geology with seismic interpretation. The amplitude terms can be classified as bright spot and dim spot. The bright spot are local increase in amplitude on a seismic section caused by the hydrocarbon accumulation due to the increase in reflection coefficient at the top and bottom of a reservoir caused by the gas presence in the pore space. DHI, a measurement which indicates the presence or absence of a hydrocarbon accumulation. It can be classified as a bright spot, dim spot, flat spot, shadow zones, etc. The topic which is introduced here is AVO, or amplitude variation with offset. The variation of amplitude of a seismic reflection within a trace source receiver gather is studied in order to understand whether the amplitude is increasing or decreasing with offset. We have magnified this portion on a pre-stacked data, and we can see that when we see the CDP gathers, this is the trough and the peak. We see the variation of amplitude across the CDP gathers in order to understand that a bright spot is present. Notice that amplitude indicated at the zone shown by an arrow this is the zone shown by an arrow, which talks about that what is the quality and quantity of amplitude. We have talked about bright spot. We will talk about flat spots and dim spots. Flat spots are nearly horizontal reflectors that cross existing stratigraphy, possibly indicating a hydrocarbon fluid level within an oil or gas reservoir. Dim spots are low amplitude anomalies. Now we have seen that amplitude increases with offset. There can be amplitude which are low amplitude anomalies. As we understand, the word anomaly means that any change which happens than that of the background. So we as explorationists are looking always for anomalies. The polarity reversal can occur where the capping rock has a slightly lower seismic velocity than that of the reservoir and the reflection has its sign reversed. It should be noted, which is shown here in red, for a dim spot to occur, the shale has to have a lower acoustic impedance than both the water sand and the oil and gas sand, which is the opposite situation required for a bright spot to occur. Now here is an example of a bright spot, polarity reversal and dim spot. The red talks of impedance increase, the blue talks about impedance decrease. Here is a scenario where we have shale, oil and gas sand and brine sand. It is true, as a plot against impedance by depth, we can see that where the bright spots are, we can see where the polarity reversal talks about the presence of a gas, and then we can see dim spot on the third bracket where we can see that the impedance in the shale is lower than the oil and gas, and the brine sand has impedance more as we go deeper.